Hello students. Our next topic is magnetic potential energy of a nucleus. How a nucleus gains some magnetic energy. So what is magnetic energy? When a nucleus whose magnetic moment has a Z component mu Z is in a constant magnetic field, then the magnetic potential energy of the nucleus is Um is equal to minus mu ZB. So mu Z is the magnetic moment, the component of magnetic moment along the direction of the magnetic field. So minus mu ZB is the amount of magnetic potential energy gained by that nucleus in the particular magnetic moment. So this energy, magnetic energy, is negative when magnetic moment and magnetic field mu and B are in the same direction. Okay, now this energy is positive when magnetic moment and B are in opposite direction. So when mu and B are in opposite direction, the energy will be positive. So when each angular momentum state, consider any angular momentum state of the nucleus, it splits into components. This is similar to the Zeeman effect which we have studied in our atomic electron states. So because of this magnetic energy, each angular momentum state splits into its components. Now this is the energy level diagram. This is the energy of the nucleus when magnetic field is 0, and this is the splitting of that energy level into 2 when B is greater than 0. Okay, this is the case of a proton. The energy level of a proton in a magnetic field are split into spin up. What is spin up state? Spin up means ms equal to plus half. When ms equal to plus half, you get E is equal to E0 minus mu PZB, because ms is positive and mu and B are in the same direction. So Sz is parallel to B, both are in same direction. So the energy is decreased by an amount mu PZB. Okay, and the other cases when ms equal to minus half, the spin down state. So when the spin down means Sz anti-parallel to B. Okay, then the energy will be E0 plus mu PZB. So it increases by an amount of mu PZB. So the energy difference between these two levels is 2 mu PZB. So if a nucleus is in the spin down state and it emits amount of energy this much, it will be flipped into this lower state. And if a nucleus in spin up state, it gets an energy of this amount, it will be excited to the higher energy state, which is the spin down state. Okay, so the energy difference between the sub levels is delta E is equal to 2 mu PZB. Okay, a photon with this energy will be emitted when a proton in the upper state flips its spin to fall to the lower state. A proton in the lower state can be raised to the upper one by absorbing a photon of this energy. Okay, and we know that the photon energy is E is equal to h nu. The photon frequency nu L, frequency nu suffix L, that corresponds to delta E. The amount of frequency nu L is equal to delta E by h. That is equal to 2 mu PZB by h. This frequency is called the Larmor frequency for protons. So Larmor frequency means this is equal to the frequency with which the magnetic dipole, any magnetic dipole, precesses around a magnetic field. Okay, if mu is the magnetic moment, in a magnetic field it precesses around the B field. A nuclear magnetic moment mu precesses around an external field B with a frequency of, which is called the Larmor frequency, which is proportional to B. That is, this is the frequency with which magnetic dipole precesses around the magnetic field. So this name, it is named after the scientist Joseph Larmor, who derived this equation for an orbiting electron in a magnetic field, which is generalized to any magnetic dipoles. So any magnetic dipoles with this frequency is termed as Larmor frequency, which is named after the scientist. Okay. Now we can go through a problem. You do it in your notebook. To find the energy difference between spin up and spin down state. We can take this equation, delta E equation, and find out the value, and also find out what is the Larmor frequency of a proton in this field. What is the frequency in this field? So we can take the equation mu is equal to delta E by h cross. You do it in your notebook. Next is nuclear magnetic resonance, or NMR. So consider a sample of substance that contains nuclei with spin half in a magnetic field. So a substance which contains a nuclei of spin half in a magnetic field B. Okay. Now the spins of most nuclei will align parallel to B. Why? Because it is a spin up state. Parallel to B means it is the spin up state, which is the lower state, which I have discussed earlier in the figure. You can find that the spin up state is it is having the lowest frequency and lowest energy. Okay, lowest energy. So most of the nuclei will align parallel to B. Okay. Now if we apply an electromagnetic radiation of Larmor frequency to the sample, what will happen? The nuclei will absorb that amount of energy required and will flip to the higher state, which is the spin down state. Okay, this phenomena is called the nuclear magnetic resonance. So, what is nuclear magnetic resonance? So, in a sample containing nuclei of spin half, when we apply an electromagnetic radiation of a particular frequency, Larmor frequency, to that sample, the nucleus will flip from the lower spin up state to the excited higher state, which is the spin down state. This phenomena is called nuclear magnetic resonance. Right? Now what are the applications of NMR? First, we can find the nuclear magnetic moments experimentally by using this technique of resonance. One of the method is that when we apply a RF frequency supplied at a fixed frequency by a coil around the sample, and B is varied. Okay, so we are in the equation nu L is equal to 2 mu P Z B by H cross. We are fixing nu L and varying the magnetic field. So at the particular frequency, when it matches with the Larmor frequency, that absorption will be the maximum one. So from that experiment, we can find out what is the magnetic moment. Or you can do that same process in the reverse manner, that is by fixing magnetic field and varying the frequency. Okay, so that is one of the application. You can find out the magnetic moments. Then the second application is that since the electrons around the nucleus partially shield the magnetic field on the nucleus. Okay, thus helping an increase in relaxation time of the nucleus, so that we can study the nucleus structure and all. The relaxation time is increased by the partial shielding of the electrons outside the nucleus. Okay, this is one of the application. Then another application is that NMR imaging method has a higher resolution than X-ray tomography. It has a higher resolution. Next is NMR imaging is safer because RF radiation has less energy and hence it won't harm our living tissues. So it is a safer method of imaging. Okay. Now other application is that it helps to study the chemical structures and reactions. How is it helping to study the chemical structures and reaction? We can go through an example. For instance, the hydrogen nuclei in the CH3, CH2 and OH groups has slightly different resonant frequencies in the same magnetic field. All of these frequencies appear in the NMR spectrum of ethanol with a ratio 3:2:1 of intensities. Now, ethanol molecules are known to contain 2 carbon atoms, 6 hydrogen atoms and 1 oxygen atom. So, they must consist of 3 above groups linked together. Okay, so the formula can be written as CH3CH2OH. Thus, better represents methanol than C2H6O, which merely lists the atom in its molecules. So, on a representation of this chemical formula has least significance compared to this representation. This representation is identified by the NMR spectrum of ethanol. Okay, so the intensity ratio 3:2:1 corroborates this picture since CH3 group has 3 hydrogen atom, CH2 has 2 and OH has 1. This is how we can study the chemical structure, or we can improve the chemical structure of the elements or the compounds in certain cases.